higher order derivatives, horizontal tangents, and more applications of the derivative. Alright, so higher order derivatives meaning just taking multiple derivatives. So the derivative, when we say find the derivative, f prime of x, which represents the change in y per change in x, when we take the derivative with respect to x, it's the instantaneous rate of change of whatever our original function represents. That's how fast or slow it's either growing, increasing, or stopped. Graphically, that slope is represented by tangent lines. Right? Graphically, it's the slope of the tangent lines to the original function. It's the velocity of the original function. Right? Rate of change, how fast. And what direction, right? Velocity is how fast something's moving, and positive and negative means what direction it's moving in. Well, what we can then do is, we can take a derivative of the derivative. We can find the rate of change of the rate of change. How is my speed, my velocity changing? Is my speed getting faster? Is my speed getting slower? Right? How is the speed behaving? Well, we do that with a second derivative. Right? The second derivative finds what's called the acceleration of the function. It's the how fast or slow my change in my function is changing. The best way to describe it is, again, it's just like when you're driving in a car and you hit your accelerator, right? Or you hit your brake, right? Your velocity, right? Your speed that you're traveling, your miles per hour, goes up when you hit your accelerator, right? Your speed increases, you're accelerating. When you hit your brake, right? When you hit your brake or you take your foot off the gas pedal and just inertia and stuff slows you down, um, that's deceleration, so it means your velocity is decreasing. Right? And so that's what this represents. Now, this is more in terms of an application. Is my, if my function represents cost, are my costs increasing? Is the rates of cost increasing? Are the rates of cost decreasing? Right? And you do that by just taking the derivative of the derivative, and we call that the second derivative. All right, the notation for it, if it's function notation, we just do two primes. Double prime means I've taken two derivatives with respect to x. The rate of change notation means d squared, which means the derivative twice of my function y. Dx squared, which means respect to x twice. All right, that's why when we have acceleration, it's so the best way to sort of think about it is in terms of velocity. If your velocity is miles per hour, your acceleration would be the change in miles per hour squared, right? Because I'm the square of that function is changing with respect to that a second time, so it's the square. All right, so that's sort of giving away your notation. It's the change in y with respect to the change in s twice, so it's squared. All right, so a simple example. So suppose this is my original function f of x, which is the polynomial 3x to the fourth minus 6x to the fifth. Find the second derivative. Well, in order to find my second derivative, I need my first derivative. Well, my first derivative, these are just simple power rules. So this is going to give me a 12x cubed minus 6, right? That's my first derivative. That's my velocity. And then my second derivative of my function, so second derivative of my y with respect to x twice, which again with function notation, which is what I typically use as the function notation. But you should recognize both notations because the rate of change notation is trying to tell you the units, how it's changing. So it's the change in my function twice with respect to the variable x twice. Okay. And so I basically take the derivative of this again. So I pull my 3 out, get 36x to the second. All right, and there's my acceleration function. All right, how fast my velocity is changing or not changing, or increasing or decreasing. All right, a few more kind of simple examples. So we're just going to, and basically I'm going to do some examples with our, fraction notation and our negative values, just so that you can see a couple of those. All right, so suppose my function is 10 times the cube root of x to the fifth. All right, so first thing I have to do is change that cube root of x to the fifth to 10 times x raised to the power 5/3, right? The fraction part is the root part. And now I take its first derivative and then its second derivative. So basically you're just doing derivatives in order. All right, so the first derivative is, well, the 10 is just going to come along. I use my power rule to get 5/3 out front, x raised to the 5/3 minus 1. which is going to leave me with 2/3. And then I simplify that because I can, actually nothing really simplifies. It's going to be 50 over 3. So it's just the fraction 50 over 3. And leave it exact. 50 over 3 x raised to the 2/3, which again, you can leave it like that, or, oops, not 10, 50. 50 over 3, the cube root of x squared. Right, well, that's the first derivative. Well, I'm going to find the second derivative. So I'm going to go look at this middle form because that's the easiest way to do it. So again, the 50 over 3 just comes along. I pull down the 2/3, and then it's going to be x raised to the 2/3 minus 1, so it's going to be a negative 1/3. And so the second derivative, if I simplify this, well, nothing really cancels here, so just an ugly fraction. It's 2 times 50, which is 100, over 3 times 3, which is 9, so it's just 100 over 9. I'll leave it. X raised to the negative 1/3, or if you want to rewrite that, that would be 100 over 9 times the cube root of x. Alright, but like I said, on tests and quizzes, it's fine if you leave the fractional exponent. Alright, let's do another example with division. So what if I have 1 over x to the 9th? Well, first thing I have to do is rewrite that as the power function, x raised to the negative 9. And then I find my first derivative and then my second derivative. And again, it's just taking two derivatives in a row. So this is just a simple power rule. Pull the negative 9 out. Subtract 1 to make sure you subtract, so it goes negative 10. Which again, if I rewrite that, that would be negative 9 divided by 10. X to the 10th. I keep wanting to write these wrong. X to the 10th. Alright, now the second derivative, again, it's easier to use the first form that I've got written here. So the first thing you do is you take your negative 10 times your negative 9, so you're going to get positive 90. X raised to the negative 10 minus 1, so that's going to be x raised to the negative 11. If I rewrite that, that would be 90 over x to the 11. Alright, and there's a few examples of the second derivative, which the first and second derivatives are the ones we use the most. I am going to go over the third derivative, but we don't use the third derivative as much. Most of the time, it's just the first and the second. Alright, we'll pick up the third derivative in the next video.